freaking idiot.
You know that one? I need to get some new movie quotes. Okay. Dark colors. The Blackbody curve for a star will tell the color of the star as well as its temperature. So sometimes you can just see the color with your eye and see that it's red, or see that it's blue, or see that it's white. This is a clue that tells you the temperature of the star. Blue means hot, red means cold. And it has to do with the Blackbody curve that we studied way back in chapter 2, which I'll show you a little graph of. Here we're looking at Orion, which is starting to get higher and higher at night. If you go out in the middle of the night and look up, you'll probably see this. Betelgeuse is a red star. It's a red giant. So that's a cool star. You can imagine a cool star. I mean, it's still thousands of degrees on the surface. But it's cooler than Rigel, which is a blue star. It's a very hot star. And these three in Orion's belt are real hot stars too. They're blue. And again, here's a visible photograph of the stars that's been color enhanced, where they exaggerate the colors a little so you can really see the colors stand out. But if you go outside and you just look with your naked eye, you can see some of the colors. And here's basically how it works. If the color is blue or electric blue, that's like neon blue, you're talking a hot star. 30,000 Kelvin on the surface, or 20,000 Kelvin on the surface. That's a lot hotter than our sun. That's about 5,800. So our sun's kind of a yellow star. And red is the coolest on the surface, maybe only 3,000 Kelvin. And this is just going along with the colors of the rainbow. Do you remember how you remember the colors of the rainbow?
Where'd you have?
Very nice.
Good job, McLean.
Red, orange, yellow, green, blue, indigo, violet. And this side of the spectrum is shorter wavelength, higher energy. And this side is longer wavelength, lower energy. So hotter and cooler. If you stick a poker, an iron rod into a fire, it'll go through this progression and it heats up. You may never get it so hot that it becomes blue or violet. But it starts out getting red and then...
It's white?
Well, white is kind of a combination of all of them.
Oh boy.
And usually if you're peaking somewhere in the middle here, you'll be white. Because you'll have some of... If your Blackbody curve, y'all remember what the Blackbody curve looks like?
Yes.
It kind of looks like this. And so usually if it's right around here somewhere, you end up with white because you're kind of getting all the colors there. But if it's a real big curve that goes like this, you got a lot more blue than you have red. It's going to appear blue. And if it's a smaller curve that goes like that, well then you only have red, so you're going to see it red. Blackbody curves. We studied that in chapter 2. Here it shows them. Here's the curve of a 3,000 degree star, the curve of a 10,000 degree star, the curve of a 30,000 degree star. You see the 30,000 has more blue than anything else in the visible spectrum, so it's going to appear blue. Now, all stars are basically made of the same thing, hydrogen and helium. But when you look at their spectra, they actually will give different spectra. And that's because of different temperatures. A 30,000 degree star spectra looks like this with these lines. A 3,000 degree star spectra looks like this with more lines. And it's not because they're composed of anything different. You just get different lines at different temperatures. Because you have electrons jumping to higher levels at different temperatures. And just basically there are different energies being given off. It took scientists a long time to figure this out, that the stars weren't actually made of stuff different, that different temperatures cause different spectra. And they did a lot of experiments here on Earth, making things hot and looking at their spectra, and they noticed that you get different spectra if you heat things to different temperatures. And at first, when they were looking with their spectroscopes at stars, they just give a spectra that was 10,000 K, they called it letter A, spectra A. And a spectra that was 20,000 K, they called it spectra B. And so they had A, B, C, D, E, F, G, going all the way through the alphabet with all these different spectra. And only after they gave it these letters, names, did they figure out that, oh, it's because they're different temperatures, not different makeups. And now that they've sorted it out, they aren't changing the letters that they gave them. So it's not in an order. It would be easy if 30,000 was called A, and 20,000 was called B, and 10,000 was called C. But it's not that way. O is the hottest star, and M is the coolest star. And if you just put a spectroscope on a telescope, you can measure the temperature of every star that you can see out there. By the telescope seeing the little lines, it can figure out the temperature of any star you can see. As long as the light gets to you, it'll have a spectrum. And you have to memorize the order of these letters. And I'm going to give you an easy way to do it. You ready?
Mm-hmm.
Oh, be a fine girl, kiss me. Or, for ladies, if you prefer, oh, be a fine guy, kiss me. That's the way to remember the order of the star spectrum.
What a goat.
Oh, be a fine goat, kiss me.
Or ghost.
Oh, be a fine ghost, kiss me.
Wait, this is the order of the...
This is the order of the spectra of stars according to temperature, going from hot to cold. So a type O star is the hottest star, and a type M star is the coldest star. And you know what our sun is? Can you tell?
Is it K?
Nope.
M?
Nope.
G.
It's G. We're a type G star. Our sun is type G. Here we go. Oh, be a fine girl, kiss me. The sun is actually a G2 because they also give numbers for the spectra. So, the way the numbering system works is each letter has numbers 0 to 9 as you go up in heat. Let me make sure I'm telling you this right. So I get confused sometimes. The lower the number, the hotter the star. So you have G0 is the hottest G.
Yo, G.
Oh, jeez.
And G1, G2, G3, G4, you're getting cooler as you go down in numbers. So, after G9, that's the coolest G star. Then you go to K what? What number?
9.
The hottest K is K what?
0.
Nope.
0.
1.
0 is the hottest, 9 is the coolest.
9.
All you have to do is pay attention and think about this and you'll have it. You don't even have to study it.
Oh.
0 is the coolest.
You just said 0 is the hottest.
0 is the hottest. 9 is the coolest. So G0 is the hottest G. And it goes all the way to G9. And then you go to K0, all the way to K9. And then M0, all the way to M9. So, what's the hottest star? If you had to give it a letter and a number.
M-O.
M0 is not the hottest.
M0.
Double O.
Look at it.
Oh,
Double
sorry.
Blank.
O.
O is the hottest. And what's the hottest number?
You said 0.
0 is the
Nine.
hottest number. So
Oh, nine.
O0 is the hottest star.
Oh, 0.
I said O0.
No, you said M0. Makey Sensei, what's the coolest star? Do it, Olivia.
That topic this morning.
Whoops. So what are we?
G2.
We're a G2, like Gatorade 2.
We'd be a juice.
We're G2. Now, how do you tell how big a star is?
With a tape measure.
Well, some stars can be measured by angular size. For instance, we can look at our sun, and we know our sun is this wide on our telescope. And if you take the width of the sun and go back, there's a small angle there. We call that angular size. The angular size of the sun is about 1 degree. That means if the sky is 180 degrees, the sun takes up
Bless
1
you.
degree of angle. So does the moon. They're both about 1 degree. I think it's actually a little less than 1. So, what about a star further away? Well, it's going to have some angular size too. The nearest stars can be measured by angular size. It's a very small angle, but we have the ability to measure nearby stars by angular size, and we can tell how big they are. This is Betelgeuse. Betelgeuse is a red giant, and this is Betelgeuse seen through the Hubble telescope.
You said it 3 times.
I said it twice, didn't I?
No, you said it 3 times.
We're in trouble. That's a reference to the movie Beetlejuice.
Oh.
You say Beetlejuice, Beetlejuice, Beetlejuice. What do? You're
He comes out.
shipped off? The monster comes out?
Beetlejuice comes out.
The ghost? So anyway, you can tell the size of this star just by measuring its width through your telescope. That's an angular size. And we know Betelgeuse is huge. It's called a red giant. But we can also tell the size of a star by its brightness. So you got to think about this now. The larger a star is, the more luminous it is. That means if a star's bigger this way, it's going to be brighter. Because there's more area giving off light. Okay? Don't just write this down. I want you to think about it too. The hotter a star is, the more luminous it is. So if a star is blue, it gives off more light than if a star is red. Red stars are usually a bit dimmer. So there's 2 things that play into brightness. How big the star is and how hot the star is. So the brightest stars would be big and blue. And the dimmest stars would be little and red. Are y'all with me so far? Let me give you an example. Okay, so if we know the size of the stars, or we know the distance of a star, and we know the color of a star, because you can see what color it is by the spectra, then you can figure out how big it is. If you know any 2 of those 3 factors. And here's an example. If a star is relatively cool, it's a cool star, so we're talking kind of reddish, and it's far away, We can measure the distance to it, so we know it's far away. We measure the distance by triangulation, or there's other methods. So we know the star's far away, and we know it's a cool star, and it's red. But it appears very bright. It's cool, and it's far away, but it's bright. What do you know about the star? It must be big. That's the only way it could be bright. Do you see? So if you can see the color of it, and you know the distance of it, you can figure out the size. And so not only are they charting on this big computer where all the stars are, they're feeding into the computer the color of the star and how big the star is. Our sun is an average size star. There are stars that get a lot bigger than our sun, and there are stars a lot smaller than our sun. We call the biggest stars giants, and we call the smallest stars dwarfs. And here's an example of a bunch of different type stars. Here's our sun. That's how big our sun is. And they've just taken this box here. That would be our sun. And they've blown it up big so you can see it. There's our sun. There's how big Jupiter is compared to our sun. Now, Jupiter's a planet. But that's how big Barnard's star is. That's the real fast-moving star. It's 0.2. That symbol right there, you have to learn this symbol right here. That means solar radii. That means it's 2/10 as big as our sun. It's 20% the size of our sun. 0.2 solar radii means the radius of this star is 0.2 the radius of our sun. Our sun is 1 solar radii. Look at that little star. It's called Sirius B. Are you serious, B? That's some street language. I got a lot of street cred around here. That's St. Simon's. Sirius B is only 0.1 solar radii. And Proxima Centauri is only 0.08 solar radii. That's 8 times as big as Sirius B, but it's a little star. Question?
So a gas giant can be bigger than a star?
Yes, Jupiter is a gas giant that's bigger than a star. It's bigger than some stars. And we'll learn about why that is.
So if we could stand the intense heat, we could go stand on a star without being crushed by the gravity?
Well, here's the problem, is these stars that are real small are incredibly dense. And so they'll still have a lot of gravity and would still crush you.
Oh, darn.
We're going to learn about the life of a star and how these little stars form. But they basically form from a star like the sun. The sun, when it dies, will expand and expand, and you'll be left with just the core of the sun that doesn't expand away, and it kind of stays where it is, and it becomes very dense, and it's very dense.
Okay.
So that'll have, even though this one's 0.01 solar radii, it's 10 times smaller than Jupiter. It's probably got more gravity than Jupiter does, and at a very small size, so it would really crush you.
And what star is the big red star in the corner?
This is Antares. This is a red giant. It's one of the bigger stars we know of. 500 solar radii. It's 500 times as big as our sun. If it were sitting where our sun is, we would be inside of it. That's how big it is. Our planet would be within the star. Question?
If there are like so many stars, is it possible that there's like a supernova like constantly, or like daily?
Oh, absolutely. Yeah. In the universe, yeah, every second.
They're not kind of like it doesn't affect us, or like we can't.
They're just so far away that we don't feel any effect. We think a supernova happens in our galaxy only about once every 100 years. And often they're at the other side of the galaxy and we can't see them. The last supernova that was within sight of us was in the 1800s, I think, or 1700s. And they usually appear as a really bright star that you can see in the daytime. Of course, it actually happened thousands of years ago, and the light is just reaching us now. You got to keep that in mind too. Yes?
Will that eventually happen with the sun when it dies and
It won't go supernova, but it'll expand, and then kind of float away. So our sun will become a red giant. Maybe not as big as this one, but maybe as big as that one. So we're going to talk about the life of a star, but this is a great video that shows the size of objects and stars compared to one another. It's kind of exciting. Hold on, let me start it over. I love this video.
Oh, I've seen this before.
Yeah.
So I made a parody of that.
This is great. That's our moon. So stars get pretty big.
What happened to Antares or whatever?
What happened to it?
Well, it didn't show it.
Yeah, it was one of those.
Are you sure?
Yeah.
I didn't see it. Okay, never mind.
It was like the fourth one.
Oh, really?
Yeah.
You're cool.
I'll show you some of those stars next time we go out to the beach.
Oh, hey. So, remember how yesterday I was telling you about the... No, never mind. That wasn't yesterday.
The star outside your window.
Yeah, stars outside my window. So, the day before yesterday, they were underneath the sun. There's two of them. One's red, one is really bright. And then yesterday, when I was outside my window, the moon was below them.
The moon was below them. Yeah, the moon moves.
Yeah,
in
but
comparison to the stars.
Yeah, but it moves a lot.
Yeah, it does. It moves a lot. Yeah. It's remember the moon's orbiting the Earth, so it moves a pretty good distance every
I
day.
just didn't expect it to move so far.
Yeah. And this is what the ancients were going, hey, the planets do that too to some extent, but they don't move as far each day. So they've come up with this device. It's called an HR diagram, where they plot on a graph the temperature versus the luminosity. Now, luminosity is brightness. If you put the luminosity on the y-axis and the temperature on the x-axis, you have an HR diagram. HR stands for Hertzberg-Russell. They're the two scientists that started doing this. And they noticed a distinct pattern. When you plotted these stars, they all ended up, not all of them, but many of them ended up along a line. So here's a plot of some of the stars on the HR diagram. There's Vega. That's the real bright one that I think that you're referring to. I don't know for sure. I'd have to see.
The one near it is red.
I'm not sure what it is.
So what was the largest one?
Rigel, Betelgeuse. Betelgeuse is huge. Antares. These are all real big stars. And notice that they're real bright. So look at this star. It's got a high luminosity, Betelgeuse. It's got a real high luminosity. It's 10,000 times as bright as the sun. But it's got a low temperature, so it goes over here. Here's our sun. It's what we call, it's one solar unit of luminosity because it's the sun, and it's about 5,800 K. So it's a yellow star. And so forth. So you can plot all these different stars according to their luminosity and surface temperature. So these are just some famous stars that we've studied. But if you start plotting a lot of these, I'm going to skip that. If you start plotting a lot of these, you end up with kind of a line where they all kind of, the stars all kind of cluster along this line in the middle. And we have a name for this line in the middle. It's called the main sequence. And most stars are on the main sequence. Most stars are at this line here. So, low temperature stars are usually low luminosities. They aren't as bright. And high temperature stars are usually high luminosity. They're usually brighter. So it's a main sequence. Now there are some stars way down here, and we call these white dwarfs, because they're real hot, but not very bright. And it's because they're so small. And then up here we call this the giant region. And they're real big and kind of cool. Here are the giants. And a lot of real big stars are on the line, but some of them go over here and become cooler. And what they figured out is there's a reason for this, for the way they're spaced out on this chart. Let's skip that too. Here we go. Look at this. This is a chart. If you just chart this Hipparcos satellite has charted a whole bunch of stars. And if you chart them like this, you find out that they kind of it ends up looking like this. And there's a reason for this. It's because during the life of a star, it's on this main sequence here. And most stars will stay on the main sequence, will stay at their brightness and temperature and luminosity for billions of years. And then when they start to die, they'll come off of this. And they'll start getting cooler because they expand in size. So the next thing we really study which I'm kind of getting ahead of ourselves here, and that's why I was skipping those things. I'm going to show them to you later. Is the life of a star, and that's what this video I'm going to show you is about. The life of a star. So you read 10.3 and 10.4 tonight, or over the weekend. 10.4. 10.4, and you can stop filming there.